Can you hear me okay?
Yeah, I can hear you.
Okay, cool. So what are we doing tonight?
My teacher gave me another math review due on Monday. I just sent an email to you. I'm not sure if it's gone through yet.
Let me open it up.
Mm-hmm.
Yep.
Okay.
Which page should I open first? The one on the right or the left?
The left is first.
I don't know if you can even see those enough to know which page is which, but we'll start at the beginning.
Yeah.
Is that big enough that you can read? You probably have it in front of you anyway, so let me get it just a little bit bigger.
Okay.
All right, I'm going to shorten notation just for purposes of writing.
Okay.
Is that all right?
Yeah.
So what is y prime?
So you have to change it to x squared minus 5x to the 1/2.
Good. Always get rid of radical signs when you're dealing in calculus. Okay.
And then you do 1/2 times x squared minus 5x to the negative 1/2.
Which is the derivative of the outside.
Right.
Now, there is an inside also. That's the inside. So you have to multiply that by the derivative of the inside.
So times 2x minus 5.
Okay. And then, are they satisfied with this answer, or do they always want positive exponents? Do they want radical signs back in the thing?
I think he wants, when it starts with a radical sign, he wants it to end with a radical sign.
Okay. And let's put it in the, tell me what to write.
So
what's in the numerator?
2x minus 5.
What's in the denominator?
2 times, and then x squared minus 5 to the positive 1/2.
Which is?
Radical x squared minus 5x.
In other words, doing both steps at once. You're right, it was x squared minus 5x to the positive 1/2 because I moved it to the denominator, but then putting it back in radical, I get that. And there's nothing further I can do with that. Can't divide top and bottom by 2 or x or anything else.
Right.
All right, this one. I knew they weren't going to leave you with just those 6 problems we did the other day.
Yeah.
That's not enough practice to cover the power, product, quotient, and chain rule.
Yeah, definitely.
All right, so what are we going to need to do here?
Okay, so we need the product rule.
Okay, it's a good start.
So 3x times negative cosine squared 2x.
No, where are you getting negative cosine squared 2x?
Oh, I mean negative sine squared.
Okay, well, let's back up here. Most of the time, figuring out the inside is relatively simple, right?
Mm-hmm.
In other words, on number 1, the inside is clearly x squared minus 5x.
Yeah.
On number 3, what's the inside?
Oh, Is it cosine?
Number
X?
three. Number three.
X squared plus 3?
Correct. Number four, what's the inside?
Root 3x.
No, 3x.
Oh.
Okay. Now, I'm going to make it tougher. What's the inside here?
Sine squared of x.
No, the inside would be sine of x. And here's how you can verify that your inside makes sense. Okay, that would make this look like sine, sorry, hold on. If I let the inside be sine x, then this is going to turn into u squared, which I know how to differentiate. In other words, if I want to figure out dy dx, well, it's going to be dy du, which I can do, times du dx, which I can do up here. This is how you get the derivative of the outside times the derivative of the inside. That's where it comes from. It actually comes from applying the chain rule. And notice why this bottom line is correct. Fractions, right? dy over du times du over dx equals dy over dx. Okay, so the difficulty becomes in identifying what is the inside. Well, in this case, if I let u be sine x, it gives me something that I can figure out dy du. Okay, change it slightly. Now what's the inside?
Now it's sine.
No. If you make u equal to sine x, there's no way to write this in terms of u. In other words, whatever you deem the inside to be, you have to be able to write the original function in terms of that inside. And this is not a bad habit to do on every product or every chain rule problem, is identify the inside very first thing. Well, u is the inside of that, but down here u is going to be x squared. Why? Because now I can write it y equals sine of u. I can differentiate that. That's cosine of u.
Yeah.
Okay? I can differentiate this one, u squared. The derivative of that is 2u. And in both cases, I can figure out what u prime is, which is the derivative of the inside. So in my thinking, if you can do these two problems, figure out which is the inside, these are the two hardest you'll ever come across. Okay, so this one and this one, make sure you know what the inside is and why.
Yeah.
Because they won't get any tougher than that. Now, what's the inside of that? There's actually a couple of them, but let's start with the main inside. This is going to acquire a double application of the chain rule, because I have that is an inside, but originally cosine of 2x is another inside. Okay, well, let's start with the outer inside first. In other words, if I had cosine of 2x is equal to u, now what I really have is u squared, right?
Yeah.
Okay, well, in other words, that's what y is equal to, is 3x times u squared. Now, apply the product rule to that. So you did 3x times what?
2u.
Okay, and u is cosine of 2x.
Mm-hmm.
But now we have to multiply that by the derivative of the inside, which is what? What is u prime here?
2.
It's the derivative of cosine of 2x.
2 sine x.
You know, I prefer to write it the way I think of it. The derivative of cosine is minus sine. Don't ever change the argument. But now we got to multiply that by the derivative of the second inside, which is 2. So u prime is minus 2 sine of 2x. That's what we need to multiply this thing by. Minus 2 sine of 2x. Now, we still only have part of the problem done. Let me erase this stuff at the bottom here. These two are extremely important. Make sure you understand why the inside in this one is sine x and why the inside in this one is x squared. Okay, is all we did was the first part of the product rule, right?
Right.
In other words, we did the 3x times the derivative of u squared. Well, the derivative of u squared was the hard one.
Yeah.
Okay, now the second part is pretty easy. What is it?
3 times the cosine squared of 2x.
Okay, now at this point, yeah, let's combine some things. You never know what you're going to find. In other words, we got a cosine squared of 2x over here. What if we could get a sine squared of 2x somewhere? Then we could factor it out and turn it into 1. Okay? So at a very minimum, I'm going to multiply the numbers. What are the numbers?
6x.
Well, you got this 2 over there also, that minus 2.
Oh, so
In other
negative
words,
12.
this is multiplication. It's not an argument of the cosine. Okay. So negative 12. And we have x. That takes care of that, and that. And then we have cosine of 2x sine of 2x plus 3 cosine squared of 2x. Now, I could do some additional factoring. And it's always kind of a question here as to how far you do your algebra. In other words, from the moment we got this as our answer, the rest of the problem is just algebra.
Yeah.
Now, I don't recognize this as any identity that's useful. However, just for the heck of it, let's factor out a 3 cosine of 2x and see what happens. Okay?
Okay.
So we're going to factor out a 3 cosine of 2x, and that's going to leave a 4x sine of 2x minus cosine of 2x. Now notice that I can't do anything special with this. There's no identity that that's equal to. Which means my factoring didn't really accomplish anything.
Right.
So I don't think your teacher would want you to go all the way to there. In other words, you want to factor it as long as you can do something else. You know, like I said, had I ended up with a sine squared plus cosine squared, I can turn it into 1, and that's a tremendous simplification.
Yeah.
But if you can't simplify it any further by factoring, well, then don't factor. That's kind of my general rule. And that's a perfectly good answer. I was even thinking that that looks like half of the sum and difference formula, but only half of it. So I wouldn't even be able to turn that into anything. All right, let's go on. So number 3, we got y equal x squared over 2x squared plus 3 quantity squared. Okay, they're really going to give us an algebra workout here, I can tell.
Yeah.
Okay, so start me off.
So first, multiply the bottom. So 2x squared plus 3 squared. The derivative of the top. So 2x minus 2 times 2x squared plus 3. And then times 4x over, times,
multiply it by the top. In other words,
right.
all this is the derivative of the bottom.
Right.
Okay.
So times x squared.
Times x squared, okay.
Over 2x squared plus 3 to the 4th.
All right. Now, I can see, and usually this is frequently the case when you've used the quotient rule, is that there's some amount of 2x squared plus 3 in this term, there's some more in this term, and there's a bunch down here. So at a minimum, I can get rid of the 2x squared plus 3. In other words, I can factor that binomial out of the numerator. Do you see the advantage of that? Is then I'm going to be able to cancel however many I was able to factor out of the numerator with one of these in the denominator.
Yeah.
Basically what I'm going to do is divide top and bottom by 1 2x squared plus 3. That one right there. Okay, let's see what we get. We do just that. Be careful about doing too much factoring at once. It really makes mistakes easier. So this gives me 2x squared plus 3 to which power?
The first.
Times 2x minus what?
2 times 4x times x squared.
All over
2x squared plus 3 to the 3rd.
Okay, cool. Now, let's look and see what else we can do. I can see that when I multiply this x squared by this x, I'm going to have some number of x cubed. And when I multiply this x on the right by this x squared, I'm going to have some number of x cubed. So I definitely see that I can simplify it down further by distributing these. So what's the new numerator? Distribute that.
So 4x cubed plus 6x.
And the right side?
8x cubed.
And now combine all of that.
So negative 4x cubed plus 6x.
And it's all still over 2x squared plus 3 squared. Now things are beginning to look pretty cool because look what else I can do. Ooh, almost so close. Makes me think I made a math error. You see why I was getting excited? It looks like you could almost end up with a 2x squared plus 3 in the numerator by factoring. In other words, if I factor out an x, they're in the ratios 4 to 6 is the same as 2 to 3. The problem is this negative sign. That negative sign really messes me up.
Yeah.
Because if I do factor a minus 2x out of the top, well, I'm left with 2x squared, but minus 6.
Yeah.
And now I can't really do anything more with this problem. Excuse me, that minus 3. In other words, there's nothing I can do with that 2x squared minus 3 divided by 2x squared plus 3. That's not simplifiable, even though it looks so close. I would have loved this problem had they made that come out perfect. If they'd have made this so it was a plus, then I could have canceled that with one more of that, and I would have really had a much simpler final answer.
Yeah.
Not that that's good or bad, it's just sweet. It's sweet when you take a super complex function and are able to reduce it to something like, 1 over x or even 1 over 2x squared plus 3. So it's always fun to be able to do it. And it actually might be possible that we made a mistake in our arithmetic, or our algebra rather. If that was only a plus 4, we'd be in business. Notice that was a plus 4, then I've got that, and now I cancel that and one of those, and I end up with 2x over 2x squared plus 3. A nice simpler answer. They teased us.
Yeah.
There they tease us when we're just learning calculus and first just learning the quotient rule. That's probably the hardest problem you've ever had to apply the quotient rule, is my guess. Yeah, because not only the quotient rule, but you had the chain rule also. And that definitely makes it more difficult. Now, what you're going to find is super difficult is when you have to take the second derivative of something where you had to apply the quotient rule to take the first derivative.
Yeah.
In other words, imagine this answer we got for a first derivative, and we were not able to simplify it. In other words, our final answer was a negative sign there and a squared there. Now imagine having to apply the quotient rule again to that.
Yeah.
Yeah, it's a nightmare. And by a nightmare, I mean what you end up with is a numerator and a denominator that always has a common factor that can be simplified. And it just becomes super tough algebra. And the next one, they're going to make easy, a nice easy function, but they are asking us for the second derivative of it. So second derivative is merely the first derivative of the first derivative. So let's find the first derivative.
So 2 times 3x to the 1/2.
And very important that you put that in parentheses. If I omit those parentheses, it does not have the same meaning.
Right.
Okay? So what's y prime?
So then, I guess it would turn out to just be 3x.
I'm sorry, what?
Oh, wait, never mind. So it's 1/2 times 2
Okay.
times
So 1/2 times 2, all right. Times 3x to the what?
to the negative 1/2.
Okay. Which is 3x to the negative 1/2, right?
Yeah.
Now, since we want the second derivative, then we certainly don't want to be messing with that by putting it in the denominator and putting a radical sign over it. Not yet, at least.
Mm-hmm.
Because then you'd have to transform it back into the way it looks now in order to find the derivative of it. So just start with this and find its derivative.
So negative 1/2 times 3x.
Okay, so the way I always do derivatives is I take that and I multiply it by the coefficient. That's the first thing I'm going to write. Minus 3/2. And then x, and then I take away one from the exponent to give me that. Okay?
Mm-hmm.
Now, put it in an answer with a radical sign.
So negative 3 over 2 times the third root of x squared.
Of x cubed.
Oh.
Like that. And you see why? In other words, this is the root, so that means square root, but then you cube the answer. And the only thing the negative sign meant was put it in the denominator instead of where it's residing now in the numerator.
Mm-hmm.
Okay? But this is not simplified either. I can take an x out of that. See why?
No.
In other words, x cubed is the same as x squared times x, right? And now the square root of x squared is x. So I can remove an x from that radical sign and leave 1 behind. So there's my final answer. Okay. And I'm presuming that they don't need you to rationalize the denominator here?
I don't think so.
You could multiply by root x over root x. In other words, you can always multiply any fraction by 1. And that would give you minus 3 root x over 2x squared.
Mm-hmm.
I don't know if that's any better an answer, but probably rationalizes the denominator. I'm guessing that they don't care about that, which means that would be your final answer. This is the same thing. I notice that frequently they don't bother to rationalize it if it's a variable. All right. So, number 5. Find all points where the graph has a horizontal tangent line. Okay. Whatever this graph looks like, what's a horizontal tangent line mean?
When the line has a slope of 0?
Yes. In other words, if my graph looks like this, there's a few places where it has a horizontal tangent line. There's one, there's another, there's another, there's another. Notice what I'm getting are the peaks and the valleys. So having a horizontal tangent line is huge. It tells you where your maximums and minimums are. In other words, in this interval right here, There's my minimum, and it's where I have a horizontal tangent line. So one thing that you're always doing in differential calculus is taking the derivative and setting it equal to 0. And wherever, remember what the derivative is, it's the slope of the tangent line. So I'm looking for where the slope of the tangent line is 0. Well, that means I got to take the first derivative. That's almost always the first step. In case you never can figure out the first step, take the first derivative of the function they're giving you. And that's always the first step. Okay, I mean, calculus can get very complicated, but one of the most basic things you always want to remember is that first derivative is slope. That's what it means. Okay, so what's the first derivative of this function?
So, 2 times 3 minus x squared times negative 2x.
Okay, now, best way to solve that, if I set it equal to 0, what's the next best step? First of all, how many zeros should I have? 3, is that what you said?
Actually, 4, because
No.
of the x.
No, to figure out how many zeros, take your highest degree variable that you're going to end up with. It's going to be x cubed, correct?
Mm-hmm.
That's how many zeros you're going to expect.
Oh, okay.
In other words, if you have a cubic, it cannot have 4 zeros. It can only have 3. Sometimes it'll only have like 2, where one of them is multiplicity of 2. But you can never have more zeros than the degree of the polynomial. So one thing you might think would be correct would be to multiply these 3 terms out. But that's just going to make the problem harder. In other words, if I multiply these 3 terms together, I'm going to end up with a cubic function. And while you could put that into your calculator and find the 3 zeros, there's a far easier way to do it. I'm halfway there now. In other words, I've got it almost fully factored. Can I factor that right there?
No.
Actually, you can. They don't teach you this. And in fact, they go out of your way not to teach it to you because they always teach you the difference of perfect squares, right?
Yeah.
Well, guess what? They don't have to be perfect. In other words, if I apply the difference of perfect squares to that, I get square root of 3 minus x times square root of 3 plus x. I still have my minus 2x. And now I've got it in perfect format to find the zeros. Everything is linear. I got the product of 4 things. I can first of all divide both sides by 2. That gets rid of that 2. Now how do I find the zeros? Give me the 3 zeros.
Plus root 3 and negative root 3 and 0.
Good. Those are the 3 places in this function, not y prime, but in this function that have horizontal tangent lines. If I were to pull this up on Wolfram Alpha right now, you would see that at root 3 and minus root 3 and 0, we would have flat tangent lines. In other words, maybe it looks something like, oh gosh, that. In other words, that being negative root 3, that being positive root 3, and that being 0. In other words, this would be the original function, and I would have a flat tangent line there, another one there, and another one there. And finding a flat tangent line doesn't automatically solve the problem, but it's a great start. In other words, that's frequently the very first thing you have to do, is find the places where the original function has horizontal tangent lines, which is not that easy to do. If you look at that function, figuring out where it's going to have horizontal tangent lines is, you got to take the derivative of it and then set the derivative equal to 0 and then factor the function and then find the zeros. So there's a lot that goes into that problem.
Yeah.
All right, number 6, find the equation of the tangent line of this function where x equals 1. Okay? First step.
So, take the derivative, the first derivative.
Right, because the equation of the tangent line is going to be linear, right? A line is linear. So we want it in y equal mx plus b format, which means the most important thing we can do is find the slope. So what is the slope of the tangent line at x equal 1? Well, you get slopes from first derivatives. So what's the first derivative?
So first you have to do x plus 3 to the 1/2, or to the, yeah.
Okay.
And then you can do 1/2 times x plus 3 to the negative 1/2.
Now, notice you are applying the chain rule here. It's just that the derivative of the inside is 1, so you don't need to worry about it. But it's important to understand that you are actually applying the chain rule.
Okay.
Okay? Now, what is the slope at x equal 1? Well, I can kind of write it like that. In other words, I switch back from my y notation to f of x, essentially, where I can put a number in parentheses, and what I'm doing is evaluating that at x equal 1. And I don't need to make that look pretty. In other words, I don't need to put the radical sign back in and put it in the denominator. Just plug in x equal 1 and see if you can come up with a number for the slope.
So, is it 1/2?
Well, maybe I was going too far by saying we didn't need to make it look pretty. Let's make it look pretty. Right?
Mm-hmm.
Now what is it?
So,
It's square root of 4?
2.
Okay. So it's 1/4.
Oh.
So that's our slope. So now we have an awful lot to go by to come up with the equation of the line, because I know what m is. It's 1/4. X plus b, now all I got to do is solve for b, but better yet, let's go back and instead of using y equal mx plus b, let's use the point slope format. You're going to find out that in calculus, point slope comes in handy a lot more often than slope-intercept method.
Okay.
Okay? And this is why, is because you frequently have slope and 1 point. Well, I know my m is 1/4. Now I need a point. Well, I know my x point. What's my y point?
So you have to plug it into
the original function. You got to plug it into the original function.
So
plug in the x value for that, and you get y equals 2. So in the original function, when x equals 1, y equals 2, there's my point right there. Now plug that point in to the equation at the bottom.
So y minus 2 equals 1/4 x minus 1.
And that's the answer. There's no need to do anything more with that. That's a perfectly acceptable answer in all math circles. Unless they would have said, give me the answer in slope-intercept format. And then I would have had to finish it. In other words, distribute the 1/4 and move the 2 over. But as long as they just said, find the equation of the tangent line, this is by far the easier way to do it. In other words, notice I didn't have to figure out what B was. By using the point slope format, what I did have to do is figure out what y was when x was 1. But that was relatively easy.
Yeah.
Probably easier than having to figure out what b is had I used slope-intercept format. But you're going to find that probably this is the most common format when you're doing calculus, is point slope. And that's because you come up with slope by taking the derivative, and you usually have either a partial point or a full point. In our case, we only had a partial point, x equal 1. But from that, I was able to figure out, well, what would y be equal to when x is equal to 1? And there is my full point. All right. Number 7. Most of what they're giving you here is you don't need to understand. In other words, the fact that this model is based on a weight suspended from a string in simple harmonic motion, you could cross that sentence out.
Okay.
The key part is the next line. The height of the weight above the floor is given by height of t, where t is time, is equal to 12 sine t. What's the rest of that? Plus 6t?
Yeah.
Where h is the height in centimeters and t represents the time in seconds. What will the first time after the weight is set in motion that the velocity of the weight is 0? Okay, so here's what we have. We have a spring with a weight on it. Somebody sets this in motion, and it initially goes up, and then it goes down, and then it bounces a little bit up, and then it bounces a little bit down. Okay? Well, the height, here's the floor down here, so the height of this weight is always determined by just plugging things in. In other words, at the end of 1 second, I could figure out how high this thing was above the floor. At the end of 2 seconds, it's probably going to be a little bit higher. At the end of 3 seconds, who knows? Maybe it'll be back down again.
Yeah.
But it follows an oscillating pattern, which you know because that's what sine does. Is sine goes up, down, up, down, up, down. And the important thing to know is that velocity is the first derivative of position. So when they say, what will the first time be, they're saying, where will the velocity be equal to 0? Well, clearly at the beginning, before everything is set into motion, if you plug 0 in for t, you get h of 0 equals 0. In other words, the starting velocity is 0. It's not moving, right, until you release it.
Yeah.
Okay. Well, it's going to have a velocity when you release it, and then that velocity is positive, and then it's going to go negative, and then it's going to go positive again, then it's going to go negative. Well, they want to know where the weight stops, or when it switches from positive to negative, it's got to stop first. You can't go from going straight up to straight down without going through stopping.
Right.
So the solution to this problem is to take the first derivative, which becomes then velocity. In other words, h prime of t equals v of t equals what? What's the derivative of that function?
12 times cosine of t plus 6.
Now, I want to know where that's equal to 0, because that's the turnaround points. Whenever velocity is equal to 0, that's where the weight is dead still. Solve that equation. That's a simple trig equation.
So negative 1/2.
Okay. What? Tell me again. I didn't quite hear that.
So you would subtract 6
Okay.
from both sides and then divide by 12.
Okay. So I got minus 1/2 equals cosine t. And now solve for t. How do I figure out t if cosine t equals minus 1/2?
It's on the unit circle. So, oh boy, let's see.
60 degrees would be the first quadrant angle, but it's equal to plus 1/2 there. So you got to go to the second quadrant angle to get that one.
Is it pi over
120 degrees. That's the second quadrant, but I got to put it in radians because I can't give a time of 120 degrees. That doesn't make any sense. But a radian is a number. So I can give my time in radians, and that's fine that it's in seconds. Well, if pi over 3 is 60 degrees, then 2 pi over 3 must be 120 degrees. So that time, if I plug this in to that, I will get it equals 0. Now, there's also another place in the unit circle where this would be true, and that's at 4 pi over 3. Okay? But that's the second time the weight is 0. This is the first time, the smaller number, the lower time. Okay? And what is that number? Well, 2 times 3.14 over 3. Well, that's close to 2. 2 seconds, approximately 2 seconds. That's what 2 pi over 3 is, approximately 2 seconds, 2 seconds and change. But it is a number. And I never really needed to go to degrees. In other words, if you start with that, you can immediately go to this as an answer, 2 pi over 3. And in fact, if you put it in your calculator, that's what your calculator would give you, is 2 pi over 3, as long as your calculator was in radians. It has to be in radians, otherwise it would give you 120 degrees. But you want an answer in radians for sure, because it needs to be a number. And this is something that's extremely difficult to understand. I'm not sure I fully understand it. And that's that even though I teach trig, I teach people to be sure you separate angles from ratios. The fact is that when an angle is in a radian, it's a number. So you do actually take the inverse trig function of a number to get a number. Okay, but that's kind of an aside. Just know that's why all calculus is in radians, has to be. It doesn't work with degrees. In other words, if you took the derivative of the sine, it's not cosine if it's in degrees. Has to be in radians for it to be cosine. And all trig function derivatives are only that way if they're in radians. So you work 99% of the time in radians when you're dealing in calculus. All right, let's see. What else? Number 8. And that's weird. All of a sudden it doesn't let me expand it. How strange is that? Oh well. I can read it, and you're probably looking at it. So, okay, so the graph of f of x is shown. On the same coordinate axis, sketch the graph of f prime of x. Okay, I love this exercise here. I'm going to draw it and see if I can duplicate it closely. So this is y and x. Right below it, immediately below it, I'm going to draw y prime and x. Tell me what y prime's equal to right there.
0.
Okay, so I know it crosses, that's one of its zeros. How about right there?
Also 0.
Okay, that's another place where we know y prime has to be 0. How about right here?
0.
So I got all 3 places where the derivative is equal to 0. Now let's start over here. What's y prime equal to right there, approximately? I would call that a slope of maybe 3.
Okay.
Okay, we'll call it 3. That means that the graph goes through that point right there. Now, as I go up that slope, what happens to my slopes? Do they get smaller or bigger?
Smaller.
Okay, so I'm going to put another point there, another point there. Okay? So now, what happens to y prime when I get to the right of this 0 right there? What happens to the slopes? In other words, when I start looking at the slopes here, what's happening to them?
It's negative and it starts getting
It's negative. That means they have to be down here. They have to be below the x-axis. And it looks like they get down to maybe -1. Okay, still negative. Still negative. Now they get back to 0. Okay? And that's how you do y prime. In other words, you basically figure out the slope. You could start from the left and just go right and estimate the slope and then put a point down here after estimating the slope. But what you end up with is a bunch of dots which you can then connect as a smooth curve. Notice that once I get beyond that 0 right there, that's not a 0, but that's where that tangent line is 0. Now the slopes are all positive again until I get up to this 0 here. So every point between this point and this point has to be in positive territory. In fact, it looks very close to the slopes are 1. That's almost 1, that's almost 1, that's almost 1, and it flattens out a little bit. So it looks like it goes up very quickly to lots of 1s and then gets a little flatter. Right here, it's about a half. Finally gets back down to that where the slope is 0. And now everywhere to the right of that, it looks to be about -1. There we have it. Draw a smooth curve through all your dots, and that is the slope of the first derivative. In fact, here in the 3 minutes that we have left, I want to show you a curve I have that is one of the, I wish I could show this to every calculus student I have, because it's a curve that shows first, second, and third, or the function, the first derivative, and the second derivative. Just have to find it. Here we go. Top is the original function. The middle is the first derivative. And the bottom is the second derivative. And what it shows you here, the most important thing it shows you is these fundamental relationships between function and first derivative. Notice the most fundamental one is when the original function is increasing, first derivative has to be positive, which it is. When the original function is decreasing from this point to this point, first derivative has to be negative, which it is. When the original function has flat horizontal tangent lines, the first derivative has zeros at those two spots. And then you can look at the second derivative and pretend that it's the first derivative of the first derivative. Well, the first derivative was decreasing from there down to there. That means its derivative has to be negative, which it is. Don't confuse negative with increasing. This is increasing, but it's in negative territory. And then when the first derivative is increasing, its derivative is positive. I don't know if you've learned that yet, but if you haven't, that'll be the next thing you learn, is that When a function is increasing, its first derivative has to be positive. When a function is decreasing, its first derivative has to be negative. Okay? All right. That's a good place to stop.
Yeah.
All right, Brianna. You have a good rest of your weekend, and I'll talk to you next time.
Thanks, you too.
Bye-bye.